Okay, welcome everybody. Let's go ahead and get started here. Next Tuesday, I'm going to be out of town, so our class meeting that day will just be a video that's posted online. I'll send you an email with the link, and also I'll post it on MU Online. And the next homework assignment, homework 7, that's not due till Tuesday the 23rd. We'll be doing some work related to hydrographs. So we're going to get into that today, talking about how we can find the response to a stream. All the background information to this was in our last lecture, where we were talking about the difference between rainfall and rainfall excess and all the little things out in the watershed that have to be satisfied before there actually starts to be any flow towards the outlet. And so now we're going to talk about ways to visualize that flow to the outlet. And so any questions related to the announcements before we begin talking about hydrographs? All right, so last time we looked at this figure, and what it said is that when there's a rainfall event, and we can see here in the Hydrograph that it looks like this rainfall event, the intensity was relatively low to begin with, and then the intensity was higher. Now this is a bit strange, where they're doing this inverted bar chart, and so the bigger the intensity, the lower it goes. And they're kind of doing that so that they can have both the rainfall and the runoff in the same figure. So that's why they've got this bar chart with the bars pointing downward. And so the length of each bar is representing the intensity or the depth. Rainfall hydrographs can be expressed either way. But we have some rainfall. There was a response to that, and the different places that the water goes. First of all, remember that all of the initial abstractions have to be satisfied, and there's flow in the stream even before the rainfall begins. And that base flow is related to the slow seepage of groundwater through the subsurface prior to a storm. Now we're going to talk about a lot of different factors out there in the watershed that can affect the shape of the hydrograph, and it's related to what direction the rainfall is going in. It can be things that what portion of a watershed the storm is falling in, the shape of the terrain out in the watershed. And so there's a phrase that's in your book that I think is really telling in the way that you should understand what abstractions are. So let me give you a moment to read that phrase. If you haven't already read it in the book, then now will be a chance to read it here up on the screen. All right, so it's making the point that when the abstractions have been accomplished, and I thought that's kind of a strange use of words, but in a way it kind of tells you what the abstractions are doing, is it's all these little reservoirs that have to be filled inside of the watershed before water begins to flow overland. And so we're talking about the wetting of the leaves, the wetting of the branches, the wetting of the litter, the forest litter, or whatever it is at the surface, the filling of all the surface storage ponds and so on. And so once all those abstractions have been accomplished, as it's saying here, then the water starts to flow overland. So the hydrograph shape is affected by factors like the size of the drainage area. And we saw that in last time's lecture, where if you have a really large drainage area, remember that the hydrograph response is more muted compared to a small watershed area. If you have a really small watershed area, then that reduces the travel times so that a big burst of rainfall can have their very flashy response. You're going to see a flash flood from a small watershed, whereas in a large watershed, by the time the water has traveled so long, there's a lot more of that routing effect. Remember, we discussed the routing effect is kind of like pouring a big pulse of water into a channel and how it spreads out because of the friction that it encounters in its journey. Channel slope plays a role in the routing, and there's going to be more of a dissipation of a pulse of flow if a channel slope is relatively flat. There's going to be less dissipation of a pulse if you have a steep channel. Hydraulic roughness plays a similar role, where the smoother the surface is compared to a really rough surface, then the smooth surface isn't going to delay the flow, and they're going to have more of a distinct peak compared to the roughness that would be slowing it down. Storage inside of the channel. There can be like pools inside of a channel that have to be filled, and that would be contributing to a delay in the same way that if there are puddles inside the watershed itself. And of course, the length of the stream is kind of akin to more travel time before it gets to a point of interest and more spreading out of that normal distribution. There's other things as well, like channel density. And if you have a lot of streams inside of a watershed, then the water doesn't have to travel over the surface as long before it enters those channels. And water flows through channels a lot more quickly than it does over the surface. And so if there's a really long overland flow until it gets to a channel, then that might make for more delay and less of a peak, compared to lots of channel density means it's getting into that high-speed network towards the outlet more quickly, and then there would be a more flashy, quick response. Of course, you already know that antecedent moisture conditions are talking about the rains in the time prior to our storm of interest. And so if the watershed has already had lots of rainy weather and all the abstractions were accomplished yesterday and the day before and the day before that, then the stream response is going to be more immediate than if all of those abstractions had to be accomplished with the storm that we're focusing on now. Of course, you already know that things like vegetation can slow down the movement of water, and if we make channel modifications, that can go both ways. Sometimes channels can be modified to make them more straight, and then the water is conveyed more efficiently, and then that would increase flashiness. But increasingly, organizations are doing all that they can to make the channel conditions more like they were naturally, because the natural undisturbed stream is the one that's going to be the most stable over time. And so sometimes these straight channels are made to be meandering again, and they're trying to put in like a rough riprap along the sides of channel banks to reduce the probability of scour, and that increases the roughness, and then that will delay the peak flow. So what we're going to do is go through some of these effects and look at the effect that it has on the hydrograph. I really like these sketches a lot, and the reason why I mention it is that there's a good chance I'd maybe ask you to kind of like regurgitate sketches like this in a quiz or in an exam to show that you understand the underlying concepts. And so it's definitely not something you should memorize, but in each case you should be able to understand like what is the phenomenon, what is the force that's causing, like for instance here, slope to change the hydrograph. And so what we're seeing for a gentle slope is that because the water is traveling more slowly over this slope, that the hydrograph is going to have a more muted shape than a really steep slope. And now why is that? Because remember that when the flow arrives more quickly, then the hydrograph peak is higher, and there's less time for diffusion up and downstream. So a steep slope means the travel times are slower, and if the travel times are slower, the peak arrives sooner. So you should be able to reason through and explain, like, why does the slope have this effect? And you should also be able to remember a steeper slope compared to a gentler slope. You know, if I said, here is the hydrograph for a gentle slope that's not very steep, how would the hydrograph change if it was instead a steeper slope? Well, then what you'd do is you'd shift it to the left and make the peak higher. Okay, let's look at the effect of hydraulic roughness. And so what the sketch is showing is a relatively smooth surface that's less rough compared to a more rough surface. And so then ask, does this match what we'd expect? You know, how does the hydraulic roughness either delay the flow in the case of a lot of roughness? So there's a lot of roughness there. The water is experiencing lots of friction, And so the velocity is going to be slower. And so if the water is moving with a slower velocity, some of the water is going to be trapped down here in the cracks of the whatever the roughness is in the pores, whereas when it's less rough and there's more smoothness there, then a smaller fraction of the flow is going to be in contact with that bottom layer. More of it is going to be up top with a higher velocity profile, and so just overall it's moving more quickly in the less rough channel than in the more rough channel. Okay, storage. In some ways the storage is a little bit like the roughness, because you can kind of visualize that there are little pools in each of these boulders. You know, between the boulders, that's effectively a storage pool that has to be filled up before there's flow on top of that storage pool. So it's partly a roughness effect and partly a storage effect. But just in the case of the storage itself, this is something that we've seen before as a best management practice to try and reduce the effects of urbanization. Yeah. Mm-hmm. It's because some of the water remains in these pools. And so if we're talking about the overall volume of water, if there's little storage, then after the pulse has been through, the surface may still be wet, but the bulk of the water is arriving at the destination kind of like in a more concentrated way, whereas it's shifting it to the right because of the delay, but then the peak is lower because the water is going to seep out of this storage more slowly. So it's not like it's not that one storage is filled and then it all goes to the next one and then it's empty. It's kind of like a chain where each of these pools is going to kind of drain slowly. That's right. Yeah, there is a storm that could fill each of those pools so quickly that maybe it would have an irrelevant effect. It would be a little bit lower. But yeah, there is a scale that every kind of effect we're talking about, there's a storm big enough that maybe we wouldn't be able to see the difference between this gentle and steep slope. There's some big enough storm that maybe we wouldn't notice the difference between less rough and more rough. So each one of these could be overwhelmed by just like that 500-year storm. But I mean, as a general trend, the more storage you have en route between the watershed and its destination, the delay and the reduced peak is what you'll observe.
I know, like, this is the idea of dams, but, like, what's a smaller scale of this happening in real life?
It would just be a channel that isn't going downhill at a uniform slope. So in a regular slope channel, and that's how most natural channels are. If you go up in the mountains, you'll notice, they just kind of are irregular in their downhill, and so this little pool is going to be filled here, and then this little pool is going to fill here, and so the irregularity of the slope, we're talking partly about gentler versus steeper, but then this would have a lot more storage, even though it's going from point A to point B. If there was a similar channel that had the same slope, and so it's not so much that it's not as steep, it's just that it's less irregular, then there wouldn't be the same amount of storage in there. So that's a great question. It can just be natural features, and here it's meant to look engineered, but it doesn't necessarily have to be something that's inbuilt. It could just be the characteristics of the stream itself. And that goes to, what is the stream got in it? Is it going to be sand and like silt? Well, you're probably not going to see a lot of irregularity due to sand and silt. When you see a lot of irregularity, it's because of rocks, like the differential scour and movement of rocks. Like if you got a big boulder here, and then like some smaller gravel there that was moved downstream. And so you see that like in the new river, there's a lot of irregularity to the channel slope in some spots, and that's why people are rafting there, is because it's the rocks that cause those big drops. The sudden drops in elevation is what gives you the rapids that are kind of exciting. I went whitewater rafting this summer, and we got tossed out. Our boat was upside down on top of us, and this is one of the rapids where the guide says, if you get tossed out, you got to get in the boat quick, because then there's more rapids downstream. So it was exciting. That's why it's fresh in my mind. So yeah, those features, as they call them, are because the rocks give irregularity to the channel slope. Whereas you're not going to see that in the mud river. Nobody is whitewater rafting in the mud river, right? It's because it's just mud. The channel is pretty uniform. It's pretty gentle. But if you've got rocks and steeper slopes, then there's more potential for storage and more potential for recreational excitement. All right. So drainage density is where we're talking about there being a lot of streams draining a network, a watershed. So if I draw like a little watershed here, a low drainage density would be just like there's a main channel and maybe a couple of branches. And so if we have a low drainage density, then it's going to take longer for all of the water to make its way towards the outlet, because this raindrop has to flow over land, which is slow, before it finally gets into this high-speed network that it can travel with a more rapid way. But high density means we have lots of little tributaries that extend into the network, and so any particular raindrop is going to be able to jump into a channel more quickly than it otherwise would. So that's the relative effect. Is high density means higher peaks that arrive sooner, low drainage density, lower peaks that arrive more slowly. And finally, channel length. They haven't made this very obvious, but a shorter length channel, higher peak that arrives sooner, longer length channel. I guess the reason why they haven't made it like that dramatic is that once it gets in the channel, the flow is pretty fast. And so like the real delay is in overland flow. That's like if we look at the travel time in most watersheds, once the water gets into a channel, it's just going to be a series of minutes. Whereas when the water is flowing over the land, it's a much longer time. And so I guess the reason why these two peaks look pretty much the same, it's kind of a more subtle difference, is they're going after the fact is, shorter length is going to mean it arrives sooner and it's a little bit higher, but relatively speaking, the difference is less dramatic than cases like the drainage density, where the main difference arises because of an increase in overland flow time. Are there any other questions about these effects? Okay. Now, the timing of the rainfall can have an effect on the hydrograph shape. So compare these two storms. The storm on the left, most of the water arrived early, whereas the storm on the right, there was a little bit of rainfall, and then the majority of the precipitation occurred late. And so what you can see is that the stream response is directly related to the rainfall. When the rainfall is front-loaded, the peak comes early. When the rainfall is later, then of course the peak comes later as well. So sometimes you'll look at flow data in a watershed, and the hydrograph looks different from some storm that you were looking at months or years earlier, and you wonder, like, why does the hydrograph look so different? In the 24-hour period, they were both 3-inch storms, but then it's often because you may have daily precipitation data, but the 3-inch storm from last year could have been completely different from the 3-inch storm this year. Last year's storm could have been one where of that 3 inches, most of it was in the morning, whereas this year's storm, maybe the 3 inches was mostly in the afternoon. And so the stream response could be dramatically different just because of the temporal distribution. So temporal distribution means the variety in amount over time. Now this one is pretty important too. If it's only raining on part of a watershed, then the amount is going to be less compared to if it's raining over the entire watershed. But then there's also an effect of timing. So I think the amount part is obvious. You know, there's less rainfall, so there's going to be less runoff. But it also causes, relatively speaking, a delay in the peak. Because think about how far each raindrop had to travel to get to the outlet. In Storm B, some of the raindrops fall in the watershed very close to the outlet, so they didn't have to travel very far. Whereas in this Storm A, the storm happens to be in the furthest reach of the watershed. So before those particles get to the outlet, it's got to flow over the land and then through the network before it finally arrives. And so that's the cause of why the peak is further to the right for Storm A, is the location of where the drops fell and the transit that it has to take to get to the outlet. All right, now this effect is maybe trickiest of all. And this is something that you often can't see in the rainfall data. And this, you know, when we talk about variability, sometimes just the hydrograph that you're looking at, the historical flow data from a watershed, looks different than you were expecting. So what this is saying is consider two different cases. In one case, the storm was falling on the watershed, and these are both the same amount. Both storm, the first case where the storm movement was from A to B, and when the storm movement was from B to A, the amounts were the same. But what changed is when the rain is going from A to B, those first raindrops are pretty close to A, and so they don't have very far to travel before they get to the outlet. And what they're effectively doing is they're making the channel wet even before the particles get to B. And so in the case of the opposite direction, consider when the storm was going from B towards A. Not only do those first particles arrive at the furthest part of the watershed, but the stream is dry. When those particles are making their way into the stream, it's kind of like that front of water is going through a dry channel. Whereas in contrast, when the storm was going from A to B, as the clouds were moving over the watershed, you know, the rain was wetting the stream, so that when the water finally did get to location B and those drops started making their way towards the outlet, all of the abstractions had already been accomplished. And so it's kind of like the travel time was less when the direction was from A to B, even for the particle that first landed at B. So in the case of the movement from B to A, that raindrop that falls at B, maybe it took 30 minutes. But you put that same raindrop at B when everything else downstream is already wet, and maybe it only take 20 minutes to travel instead of 30. Austin?
So the difference in these two peaks here, could you call that like the abstraction time?
Well, it's partly related to the abstraction time, but it's also partly related to how quickly the storm was moving.
Okay.
So there's two effects that are playing there. Yeah, but one of them definitely is the effect of the abstractions. This is a really important one because we sometimes think about, like, it rained on the watershed, but the clouds are always moving. I mean, it's very unusual for there to be a storm and the storm just stays in a spot. That's what made this recent flooding in South Carolina so catastrophic, was like when the hurricane came, everyone was talking about how it kind of like stalled on the Carolinas, and it was just raining and raining and the clouds weren't going anywhere, partly because there was so much of it. That was the exception. The rule is that the storms are moving around, and so it's not just always the amount of rainfall you got, but what path it took relative to the shape of your watershed. Okay, so let's revisit the definition of rainfall excess. We start off with a hydrograph. This hydrograph isn't inverted in this case. This is just we're looking at, over time, what was the rainfall intensity. Now, rainfall is not the same as rainfall excess. If we subtract out the infiltration, remember the declining potential rate of infiltration, where the infiltration rate is getting lower over time because the suction pressure beneath the soil is decreasing. Those voids, as they become closer to saturated, are going to be drawing the water down with less intensity. And so the infiltration rate is decreasing. So anything that's above the amount that was infiltrated is the rainfall excess. And so we could do like a little mass balance and remember saying a rainfall excess is rainfall minus infiltration. So it's the rainfall excess that is the water that is going to accomplish the abstractions and then contribute to runoff. So what this is saying is there is a kind of like a conceptual workflow. If we want to start with rain gauge data and we want to end up with a hydrograph, what are all of the factors that have to be accounted for before you can draw a hydrograph that shows the expected stream response? And remember, why do we care about the hydrograph? Because the peak of the hydrograph is what we're going to use to size infrastructure. The hydrograph also we have to size storage like ponds. So it's not just the peak that matters to hydraulic designers, it's also the overall amount over time. Because if we're going to be designing like the size of a pond and how big the outlet from the pond needs to be, then we're going to have to know the entire temporal distribution of runoff from the watershed. Okay, so we start with a rainfall hydrograph, and then we subtract out the infiltration. We also consider the abstractions, other abstractions like the wetting of plants and the wetting of surfaces, and then we have some idea of what's the rainfall excess. Now, of course, we've already talked about why infiltration decreases over time as the voids begin to fill, and we already know that a hydrograph is the runoff, a hydrograph is a representation of the rainfall. Now here's the conceptual analysis steps that we go in. We start with the rainfall. We've talked about how we get to a rainfall excess hydrograph. Now we have to convert this to runoff, and the simplest way of doing it is what's called a unit hydrograph approach. That's what's going to be the main focus of the rest of our time together today, is this unit hydrograph approach. And what a unit hydrograph approach is, essentially, is we're saying for 1 inch of rainfall excess, what will the watershed response look like for 1 inch? And then if we know for a given watershed what happens when there's an inch of rainfall excess, then we can predict what the shape of the hydrograph will look like for other amounts. We'll use that to scale. Now we know that there's other effects, like there's so many other effects besides just the rainfall amount. But the simplest way is just to start with characterizing the response of the watershed to 1 inch of rainfall excess, and then using a scaled approach that we've got an example we'll go through to try and predict what is the hydrograph from that. So we use this unit hydrograph approach to tie together the rainfall and the runoff. It's kind of like the proportionality factor. The output is going to be the hydrograph, and then on top of the response to the storm, we move the hydrograph upward to account for base flow, which is the groundwater that's going to be in the channel anyway, whether it's dry or whether it's wet. And so then that gives us the total runoff hydrograph. The total runoff hydrograph will be the storm response water plus the groundwater that's going to be in the channel due to just the slow movement of water through the soil towards the channel. So conceptually, this is what we want to do, is we want to start with rainfall data and end with discharge data. And the simplest way to do that is with the unit hydrograph model. So it's a linear method of scaling the runoff according to starting with an effective unit of rainfall. And so here it's in terms of a millimeter. You could say, for a millimeter of rainfall excess, what does the hydrograph look like? You could do it for a centimeter. You could do it for an inch. Just some fixed quantity of rainfall excess. You figure out what does the shape of the hydrograph look like, and then if you had twice as much rainfall, what you do is you just double the height of the hydrograph. You wouldn't do anything in this unit method. We don't do anything to change the timing of it. We just assume that if there's one, in this case it's saying millimeter, so I'll say millimeter. If you had a millimeter of rainfall, this is how high it gets. If it's 2 millimeters, it goes twice as high, but the timing stays the same. So we're not making any corrections for how quickly it's going to arrive with the unit hydrograph approach, and that's one of the weaknesses of it, is that we know if it's twice as big, it's going to arrive a little sooner because there's going to be less friction effect. It's not going to be delayed as it moves through the watershed. So this is a simplification that, on the plus side of this unit hydrograph method is it's really easy to apply. But on the minus side is it misses some of the reality of how the water moves through the watershed. So the principle is once you know how the watershed responds to one storm, you can predict what it looks like for other storms. Now, it's not like you have to wait around until your watershed has exactly 1 inch of rain. It's like, well, sorry guys, we've never had exactly 1 inch of rain in this watershed, so we can't make a unit hydrograph. You make the unit hydrograph with whatever rainfall you get, you scale it down to what would have been the response to an inch. So let's say you have 1.5 inches of rainfall excess in a given storm. Well, you just divide your hydrograph peak by 50%, and then you'd find out what is the 1 inch equivalent of it. So here are some more of those assumptions. Like I said, it's easy to use, but it's assuming that during the rainfall period, there's a constant intensity of rain. So if it's not just a single unbroken rainfall intensity, we have to break it up into time increments. So we'd maybe do an hour at a time and assume a constant intensity within each time step. It assumes that uniform distribution of rainfall across the watershed, that it's raining the same everywhere. It assumes that each time increment is constant, meaning that if we have multiple pulses of rainfall, that each one of them has the same duration. And it assumes that the watershed isn't changing in the short term or in the long term. So what I mean by that is it assumes that if you have 1 inch of rain now and an inch of rain in the next hour, that the first response and the second response are exactly the same except for the time offset. Whereas in reality, the second inch of rain is going to have a different effect than the first inch of rain is, because that first inch of rain is maybe satisfying some of the abstractions. So there's some weaknesses, but it's a good starting point for translating, with the starting point being rainfall data and the finishing point being a hydrograph. It's a good place to start. So the trick becomes when you have more than just a single continuous pulse of rain, because it's pretty improbable that a storm is just going to be like 1 hour long. If you have multiple hours, then you have to combine different unit hydrographs with different precipitation pulses. And so let's say that you are using a unit hydrograph and you're going to predict the runoff during a rainfall event that's any amount other than a unit of rain. So instead of an inch of rainfall excess, it's 1.5 inches. Then what you do is you're given the precipitation amount, and you're also given the unit hydrograph, and what you want to know is what is the runoff for some other storm. Now, this is a conceptual figure that kind of shows you the calculation approach to find what the hydrograph looks like. But I want to jump just ahead for a moment. We'll come back to this one. This diagram shows the watershed. this figure is showing the calculations you'd use to find the runoff. So let's look at the watershed first. So inside this watershed, if there was an inch of rainfall excess, this is the hydrograph that we'd see. So this is the unit hydrograph, this table on the right. Now, this watershed, I've divided it up into bands. Area 1, which is divided by this dashed gray line, this is all of the water that falls in Area 1 will get to the outlet within 1 hour. So these are essentially travel time zones. If raindrops fall in Area 2, then it's going to take some time before it gets to the outlet, because anything that falls in Area 2, it has to travel down through Area 1 before it gets to the outlet. So then Area 3, you can see, is even further away, and so on and so forth. So the rainfall, this 1 inch, it all happens in the watershed from time 0 until time 1. So I guess I should clarify this. Response to 1 inch of rainfall excess during the time 0 to 1. Okay, so the rain happens from 0 to 1, then the response is that at time 1, the flow rate is 10, at time 2, it's 100. Now, why would it be bigger than it was at 1? Because the rain has stopped by now. Like, the rain is only going from 0 to 1. So what we're seeing is at time 1, which is the instant that the rainfall stops, the flow rate is 10 CFS. So why is it higher during at time 2? If the rain stopped, why are we seeing more flow? It's the previous tributaries. It's the upstream area. So if you look, Area 2 was bigger than Area 1. So all of the water in Area 2, it took some time to get down there. So we're seeing there's a delayed response. If we were thinking about doing a graph of the Hydrograph and the Hydrograph, just briefly, it would look like this. There is, during hour 1, 1 inch of water. So here's time 0, 1, 2, 3, 4, 5, and so on. So it goes 10, 100, 200. I guess this isn't to scale very well. 10, 100, 200, 150, and it's tapering down back to 100. So the rain stopped at hour 1, but it's taking a long time for the rest of the basin to drain. Just think about, you pour water and stuff, it takes a long time for all the water to drain out of it. Even if just the period that the water was being applied to the surface was relatively short, it just takes a long time for the water to move through the watershed. So if we go back to this, what it's saying is, what if it rains for more than 1 hour? This is the response for 1 hour of rainfall. Well, what if there's precipitation not just during a single hour, but what if there's also a certain amount of rainfall that occurred during hour 2? What if it rained during hour 3 as well? So this is kind of like a conceptual equation that's showing you what would be the total runoff hydrograph if there was 3 different hours of rainfall. So what we're going to take a look at in this example that we'll go through together is, for this watershed and this unit hydrograph, then what if it was raining for 4 different hours? We're going to go through the process of applying a unit hydrograph to a rainfall where there's 4 different time increments of rain. So this is the calculation approach if there's 3 periods of rain. So what we see is the first block of the hydrograph is the precipitation amount during hour 1 and the unit hydrograph amount during hour 1. Now look at the second block. It's saying the precipitation amount, unit hydrograph 2. That's because what we're talking about now is the water that was in band 2 of that diagram. So the precipitation during the first hour, the unit hydrograph amount for the second hour, and then the precipitation during the second hour and the unit hydrograph for the first. Because there was the rain that during hour 1 was all over here. It's going to take 1 hour to get to here, 2 hours from this zone to get to the outlet, 3 hours from this zone to get to the outlet. Well, during that time that the first pulse of rainfall is moving towards the outlet, what if now there's a second pulse of rainfall over the entire watershed? And so there's like this staggered delay series of precipitation amounts that are making their way down through the outlet. Okay, so let's go through this example because I think, or at least I hope, that this idea is going to make more sense after we've gone through the calculations together. We've got an inch of rainfall excess falling onto a watershed in an hour, and we got this unit hydrograph from the inch of rainfall excess. Now, what is this watershed going to do if we get this rainfall pattern, and we're going to assume abstractions of 0.3 inches per hour? So, in other words, this is not rainfall excess yet. We're going to have to do some calculations to find out what is the rainfall excess, and then apply that precipitation into this unit hydrograph. Okay, so if you've got your computer, let's start up Excel. Okay, so first of all, let's get the unit hydrograph in Excel. So unit hydrograph, and we have the time in hours, and then the runoff. And the units of that is CFS per inch of rainfall excess. Okay, so runoff, Q. The units is CFS per inch of rainfall excess. And let me just copy and paste that over. This was our unit hydrograph. You can't copy and paste, you have to type. So this is just given. Someone out there did a study and found out what was the unit hydrograph. And with that given data, we're going to, let's calculate our hydrograph. So we'll have a hydrograph. Okay, so we had a certain time in hours. And during the first hour, second, third, fourth. Okay. And we're going to have precip in terms of inches, and then abstraction in inches, and then we'll subtract the abstractions from the precipitation, and that'll give us the rainfall excess, also in inches. Okay, so the table said that let's look at what happens if there's half an inch, then 1 inch, then 1.5, and then back down to half an inch. Okay, so there was half an inch, 1 inch, 1.5, and then back down to half an inch again. Okay, so the abstractions in the problem statement, it said it's just always 0.3 inches per hour, and that's pretty simplified. We would expect the abstractions to be bigger at the head end of the storm rather than being constant. But just for simplicity, let's assume that that was the case, that there was always going to be maybe in the form of infiltration or interception or something is just going to account for a difference between the rainfall and the amount that is considered excess. Any questions so far? This is just all given data to this point. So we're just doing the first calculation here. So equals precipitation minus abstraction, and that gives us the rainfall excess. So during that first hour, there's ½ an inch of rain, but 3/10 of it is lost due to abstraction. So 0.2 inches of rain is going to be the leftover amount that will contribute to runoff. Okay, so now what we're going to use this to determine is the resulting runoff hydrograph. All right, and so we have time in hours, and then the we'll call this like period 1, period 2, period 3, and period 4. Okay. And we got to go down through 10 hours, and you'll see why it's longer than the unit hydrograph. Okay. So each one of these is going to be the rainfall excess that we're calculating, and it is rainfall excess during the period that's shown. So maybe I'll put like kind of like a secondary description here that what we're calculating is the rainfall excess in inches during the period shown. Okay, so this is what happens when there's an inch of rainfall excess. We only had 2/10 of an inch. So what we should expect is that during period 1, there's not going to be as much rain. So there's zero flow at time 0. We have to key that in manually because it was only implied up here above. But now, during hour 1, what should the runoff be? Let's not do the calculations with Excel. Let's do the calculations with our brain. If it's 10 CFS that you get per inch of rainfall excess, but now we've only got 2/10 of an inch, how many CFS? 2. Very good. Exactly right. What about hour 2? Instead of 100, it's going to be 20. Hey, you guys see where this is headed, don't you? All right, so let's do this. Equals 0.2. And we got to anchor that reference the numbers. So I'm going to put the $sign just in front of the numbers. Well, I'll anchor the whole thing because I'm not going to be able to just copy and paste anyway. So 0.2, anchor it, times, scroll up here to the 10 because that's what corresponded to hour 1. So then that gives me the 2 CFS. And then if I drag that down, it's going to tell me how many CFS through each of those times. And then I have to just manually put in zeros for the rest. 0, 0, 0, 0. All right. So any questions about this first step?
Can you go back to your equation real quick?
So I'm multiplying the given rainfall excess for period 1 by the hydrograph. And only anchoring the reference to the rainfall amount, not anchoring the reference to the hydrograph. All right, so let me make that a bit smaller. Okay. Now let me tell you about the most common mistake that people make. Now this is what happened to the watershed during period 1. Period 1 was it rained during 0 until 1. When is it raining during period 2? That's right. It's raining from 1 to 2. So that's later than the first period was. So what we have to do is we have to shift the unit hydrograph down by 1 row. Because instead of starting at the same time as this started, we want to start the response to the event lower in our resulting hydrograph. And so we typed in the 0 in this first one, right? We typed that 0 in, so we'll put that one in here too. But then we need to put in another one. Because what we're doing is we're saying the rainfall didn't start at the beginning of the time. This now we're talking about this 7/10 of an inch of rainfall excess. And so now what we do is we start equals 7/10, anchor that reference with the $, and then multiply it by the unit hydrograph again. Okay, so starts with 7. The next one is going to be 70. If I drag this down, hopefully it'll say 70. All right. 200 times 0.7, so that'll be 140 and so on. So I drag that down through, and then I have to put in the rest of these as 0 manually. So I delayed it. I moved that hydrograph down a row because period 2 is an hour later. And so the response at the outlet, remember where we're measuring all of these runoff amounts, if I go back to the picture of this watershed, we're measuring the runoff amounts at the outlet. Let me put a little circle at the outlet. Okay, this is where we're measuring everything. All right. So the 0.5 inches of rainfall meant there was 0.2 inches of rainfall excess, which meant during hour 1 there was 20. And then all of that other, that first hour of rain is coming to the outlet in a delayed fashion, one step at a time. But at the same time as that hour 1 rainfall is making its way through the watershed, the hour 2 rainfall is also making its way through the watershed towards the outlet. So now we've got hour 2. Let's do the same thing with hour 3. So we have to type in 0, 0, 0. We have to stagger it. So we've offset it. And then we have 1.2 inches of excess, anchor that reference, times the unit hydrograph amount. And we drag it down through. And it should terminate at 60 because that's 50, the last hour of the unit hydrograph multiplied by 1.2 inches of rainfall excess. And then we put these extra zeros in. And then finally, we'll do period 4. Oh, I almost made a mistake. 0, 0, 0, 0. Okay, we stagger it, and then the first time we see the water is at hour 4. The first time we see the water coming out of the watershed from this last pulse of rainfall excess. Okay, so then the final thing is we're going to have a column that is the total runoff. So this is the total runoff, and this is in terms of CFS. I mislabeled this. I should have called this the runoff in CFS during the period shown. We were using this was the rainfall excess, and each one of these is runoff in terms of CFS. So I apologize for that discrepancy. All right, so this last one is the total runoff. And so what we have to do is we have to sum everything that is to the right, so all 4 periods. And so you're combining together the 4 different pulses of rainfall and their individual stream responses, and you're finally getting the overall delay. And so this was U1, U2, U3, U4, U5, and U6. Okay. If we're going to go back and look at that conceptual diagram, this was P1, P2, P3, and P4. Let me center that. And then this is going to be Q1. Oh, Q1 starts at time 1. So Q1, Q2, Q3, Q4, Q5. There's got to be a better way to do this. There. Nice. Okay. All right. So look at this Q1. What is essentially the equation for it? It was the result of U1 times P1. That's all that was in Q1. But Q2, that was, Q2 was U1 times P2 and U2 times P1. So if I go back to this sketch, I think this will make more sense now that we've been through the spreadsheet, that the overall hydrograph during the first hour is just the first hour's worth of rain, and U1 represents that area of the watershed that will contribute to flow in 1 hour. In the second hour, there is that first amount of rain on area 2, because it takes longer time to travel to the outlet. But there's also hour 2's rainfall acting on area 1. Okay, the third hour is hour 1's rainfall over area 3, hour 2's rainfall over area 2, and hour 3's rainfall over area 1. So actually our hydrograph was more complicated than this, because this was just showing 3 hours of rainfall and we had 4. But the procedure can be applied to any number of successive hours. It's just each time, the key that you got to remember is to stagger the arrival of the next pulse of rainfall by an hour. So there was this one, that one. There were 4 of them in total, and during each period we have to offset the unit hydrograph by 1 additional hour. Yes?
Can you go back to that bar?
This one?
Diagram?
Mm-hmm.
Well, no,
Oh, yeah.
I'm having a hard time. Why? In the second set of bars there, why do you have P1 now times U2?
Because it's the first hour of rain in area 2, because it was in the second hour, it was last hour's rain that's finally arriving at the outlet. Like, let's say
So it rains over everything.
it rains on everything
Then we
in
get
the first hour.
one. Then 2 hours later, we get the effects of.
We get the effects of what was raining here
First hour.
last hour. Yeah.
Okay.
Mm-hmm. And then in hour 3, the first hour's rain in this zone is finally making its way towards the outlet.
That makes sense.
Does that make sense for everybody? Okay. So I think in the homework assignment you have a problem where you have to do this, the same kind of unit hydrograph thing.
But that assumes that the rain from the first hour in the first section is all
Mm-hmm. Yep. Yep. You'll notice if we go back to the equation here. Yeah, so in the second hour, P1U1, that's already gone through the outlet, and it's not contributing to the flow that we see now. Like the flow that we see now is this hour's rain over the first area and last hour's rain over the next area up watershed. Yeah. You know, what's really tricky is calculating the unit hydrograph when you're given the P's and the Q's. That's kind of a really interesting process called deconvolution. It's a series of equations where you have maybe like 5 equations, 5 unknowns. It's kind of interesting, but we won't take the time to do a deconvolution as an example today. So again, the unit hydrograph idea is you use some given unit hydrograph to predict how much runoff there's going to be during a storm event that lasts other than the given duration and other than the given amount. So you can extrapolate both time and quantity to find the resulting effect. Yeah, I don't know why I'm showing this again. We've already seen all this. All right. So this is kind of the another way of looking at our answer. You know, the quantities during each hour, and this kind of shows how the pulse makes its way through the watershed. You know, by hour 5, we weren't seeing any more contribution from the area 1, because all area 1 had completely drained by time 5. But at time 5, there were other areas that were still contributing their flow to the outlet. So it kind of shows like the wave of water and where it's coming from at any given time. Like where was its original origin and what was its original time of contribution. All right, so deconvolution is the process of finding the unit hydrograph, and it's possible when you're given the flow rates and you're given the P values to then go through and calculate the U. And like I said, what you would have is a series of equations and a series of unknowns where you know Q1, you know P1, but you have to find U1, and we won't go through the process, but believe me, it's time consuming and a little bit awkward. Let's talk instead about synthetic unit hydrographs. And synthetic unit hydrographs are used when you don't have a measured response to a rainfall event. And there were enough observations that they found that there were certain characteristics of watersheds that predicted what its unit hydrograph would look like. Basically, they assessed the length of the watershed, the area, and some other physical factors, and then they found ways of coming up with a unit hydrograph when you didn't have available data. So these synthetic unit hydrographs use like geometric or statistical processes to interpolate a hydrograph when you don't have the actual measured physical data for a watershed. Now, the problem with these synthetic unit hydrographs, among other things, is that they assume a triangular runoff pattern. They assume that the water goes to some, the flow rate goes to some peak value. In the Snyder synthetic unit hydrograph method, it assumes that there's this peak, and then approximately, the time to peak is approximately 1/3 of the total width of the time is that the increasing flow rate, and then it tapers back down to 0, 2/3 of the width of the total duration of flow. And so it's kind of a process of using this triangular assumed shape of a runoff hydrograph and some physical characteristics. What you have to do is look at the duration of the rainfall, this T sub capital R, and from that given duration, you can basically extrapolate all these other processes to find out, what's the hydrograph going to be out of a watershed that you don't have any other data for. So let me just show you what is the Snyder method using this, this background information as a starting point. Let's say that we have a watershed that's 5.42 square miles, and this main stem, the main channel length, is 4.45 miles. And then there's a real strange distance parameter that you have to use in the Snyder's method, and that is the distance from the outlet to the watershed centroid. And so the reason why they're doing that is that clearly there would be a different stream response if you had a really long and narrow watershed compared to one that was very wide. And so if you have a long, narrow watershed where here's the outlet, and what they're asking for is the centroid in this, this watershed centroid. And so if this was our watershed centroid, the center of area, then the length that we're trying to measure as the L sub C, there would be a different stream response if the watershed looked like that compared to if it was a broad watershed like this, where we have the streams coming in, but where the center of area is closer to the main outlet. So you can see that these different L sub C's is going to result in different delay times, and it's going to have corresponding effects on the height of the peak. Now these regional parameters are just strictly empirical factors that were developed over time when the Snyder's method was being produced, and based on where you're located, that would just be given data. And so for this example, let's say that we have these regional parameters, C sub t is 2 and C sub p is 0.625. So the first step is to find the standard duration, because every watershed is going to have its own duration that is called the standard storm duration, and we have to calculate that before we can find the response to the storm that we're interested in. The equations, I guess I'll just put these up. They're in the book, but I'm also going to be writing them on the whiteboard here as we go through it here. So first of all, step 0, we'll just summarize all the given data. Our A is 5.42, and we have to work in square miles. The length is 4.45, and that's in miles. L sub C is 2.0 miles, and then C sub T is 2.0, and C sub P is 0.625. Okay, so the first thing that we'll do is find the standard duration. Okay, so step 1, standard duration. So T sub P is C1 times C sub T L times L sub C to the 0.3 power. Okay, so if we substitute in the regional parameters that are given, C1 is a unit factor where if we are working in traditional units, it's 1.0. For SI units, C1 would be 0.75. So C1 is 1.0 for traditional units. Okay, so it's going to be 1.0 times the C sub t of 2.0, and that is to the power of 0.3. Oh, no, sorry, I've missed something here. The L sub c's, right. The length of 4.45 miles times 2.0 miles to the 0.3 power. Okay, so 1 times 2 times 4.45 times 2 to the 0.3 power. So the T sub P is 3.853 hours. And that is the time to peak. So for this particular watershed, that's how long it's going to take until we see the peak flow rate. Now the duration, the standard duration, lowercase t sub r is t sub p divided by 5.5. So it's 3.853 hours divided by 5.5, 0.70 hours. That's the standard duration.
And does that only work for conditional use or different?
For the time? Yeah, it's the same. That's the same. No, it's just the C1 where the units would affect it.
And what was C1 for FI?
0.75. Okay, so in step 1 what we did was we found the time to peak and the duration of the standard unit hydrograph. Okay, so now step 2. Step 2, we're going to find the time for the desired duration. So there's this formula T capital sub PR it's T sub P plus 0.25 and then T sub R, capital R, minus T sub lowercase r. So this is going to be the time to peak for the desired duration. Okay. So the T sub P that we calculated before was 3.853 hours. 3.853 hours plus 0.25 times 0.5 hours minus 0.70 hours. Now I'm kind of jumping ahead. What I'm looking at here, you see in part B, it's saying find the synthetic unit hydrograph for a desired rainfall excess duration of 30 minutes. The desired duration, like if we wanted it for an hour, we'd put in 1 for this T sub capital R. If we wanted it to be for 30 minutes, then this is the desired duration is what we're substituting in there. So I guess let me start with the 1 hour duration maybe to begin with. So we'll do part A first. So we'll do 1.0 hours minus the 0.70. So for time to peak for the desired duration of 1 hour. Okay, so then step 3, we got to calculate this. And so 3.853 plus 0.2 times the difference between the desired duration and the standard duration. So that makes the T sub PR, in this case, it would be 3.928 hours. Okay. So step 3 is we're finding the Q sub PR. This is the peak discharge. And the reason why we're calculating it is it is going to tell us how high on the vertical axis we go. It's going to define the height of this point C on the synthetic unit hydrograph. So that's Q sub PR. Okay, so the formula for Q sub PR, for the formula that we have is C2, which is another units factor I'll show you in just a minute, times C sub P times the area divided by T sub capital PR. C2 for traditional units, C2 is 640. And I really wish we had a larger whiteboard. I could show you where that 640 comes from. Maybe we'll get to that in just a minute. It's a units factor. For SI, C2 is 2.75. But in our case, we're doing traditional units, and so it's 640. Okay, so then we've got 640 times the C sub P of 0.625, and then the area is 5.42 square miles, divided by the T sub PR of 3.928 hours. Okay, so now we know it's 551.9 CFS per inch. So that is the peak discharge. And then the next steps are going to be defining the T sub B by knowing how wide that triangle is. The W50 and the W75 is essentially the width of the triangle at certain flow rates of certain percentages of the peak flow rate. And so the width of the triangle at 75% of the peak flow rate, the width of the triangle at 50% of the peak flow rate. And so we've got these formulas for, in step 4, we want to find the W50, and that formula is 770 divided by the Q sub PR divided by the area, and that's to the 1.08 power. And so if we substitute that in, then it will be 770 divided by 551.9 CFS per inch, and then the area was 5.42, and all of that's to the 1.08 power. So the W50 is 5.22 hours. And the formula for the W75 is 440 divided by this same 551.9 CFS per inch and the 5.42 square miles of the watershed to the 1.08 power. So the W75 will be 2.985 hours. And the reason why we're calculating those widths is because we want to know the overall duration of the hydrograph, the T sub B. And the formula for the T sub B is based on the based on these W factors. So I'm going to have to erase this top part to do the final part and calculate the base width of our hydrograph. Okay, so step 5 now is to find T sub B. It's the base duration. So it is 2581, which is an empirical factor related to if you have 5280 feet in a mile, 12 inches in a foot, 3600 seconds in an hour, and then an empirical factor of 4. So the book goes through where 2581 comes from, but it's 2581 times the calculated amount of 5.42, which was our area. So 2581 times the area, 5.42 square miles, divided by 551.9 CFS per inch. Okay, minus 1.5 times the W50, so 5.22 hours. That was the W50, minus the W75, so 2.985 hours. So that's the W75. So if we do all of these calculations, this first term here is going to be 25.347. The second term here is 7.83. And then we subtract out the W75. So that T sub B is 14.53 hours. And the last thing that we have to calculate now is the T sub P. So we know T sub B, we know the width of that base, we know the peak, so that T sub the QPR we calculated was 551.9 CFS per inches. The T sub R in this example that we just went through, this was for a 1 hour storm duration that we have so far. And the last thing we want to calculate is this T sub P. And so how long is it from when the storm begins until the peak is observed? So capital T sub P. So this one, the T sub P will be the it's the T sub PR minus half of the storm duration. So you can see from the dimensions on this sketch that we already knew that this was 1 hour. The T sub capital R is 1 hour. And the T sub PR was 3.928. And that's, here is the T sub PR. So the last step, the time to peak, capital T sub P is 0.5 hours plus 3.928 hours. So that is 4.428 hours. All right, so we've defined everything we need to know about this hydrograph. How wide it is at the bottom, how tall it is, how long it is from when the storm starts until the peak is seen, the T sub P. Those are the three main characteristics that you'd need to to draw this triangle. How tall is it? How wide is it? And where is the peak in reference to the start of the storm? How are we doing on time? Are we wildly over time? Oh, guys, you got to warn me. We're like 11 minutes over time? Oh, geez. I don't know how I'm going to make this up to you. I think it's reparations, right? At this point, it's more than just me paying back the time. It's reparations. All right, so no class on Tuesday, but on Thursday, you'll receive your reparations. I'm really sorry to have kept you so long. This is a disaster. I was thinking more in terms of I'd bake something for you. Yeah, all right. Sorry I kept you so long. I'm going to set an alarm for myself. I just get carried away, obviously. All right, well, have a good one. I'll see you a week from today.